For our first week of investigations, the main question that we're asking is, how do arithmetic operations on complex numbers manifest as geometrically visualizable operations in the complex plane? And how can we use our intuition about the geometric properties of the complex plane to help us understand what's going on with the arithmetic of complex numbers? So we are building a real Plan B interwoven connection between arithmetic and geometry that's going to help us to understand both by understanding as richly as possible the interconnections between the two. So let's take a quick overview over the questions that you're going to be investigating this week and the interactive tool that I have for you to assist in those investigations. So main question, how are the arithmetic operations able to be visualized? In which representations are these answers the most natural? So we have rectangular coordinate representations. We also have polar coordinate representations. Some operations are easier to understand in one of those systems versus the other. And finally, how does this correspondence help us to understand and do arithmetic with complex numbers in both directions? So what operations are you going to be looking at? You'll be looking at sums, differences, and products. So addition, subtraction, and multiplication. You'll also be looking at conjugation, the complex conjugate. The reciprocal. So we're not directly going to talk about division because I want this to be as understandable as possible. So we're just going to talk about 1 over z. And therefore, we can think of division as just multiplication by the reciprocal. So if we understand the reciprocal, then we'll understand division just by multiplication by that reciprocal. So those are the main operations we want to think of: addition, subtraction, multiplication, conjugation, and reciprocals. And the question is, what relationship does the result, for example, z plus w, bear on the original numbers themselves, z and w, visualized in the complex plane? And in the back half of our investigations, we're going to ask questions like, well, under what circumstances do we know that z plus w is going to be real? What about z times w, right? When do those answers land on the real axis? What might be a general principle that we could follow? Are there ways to help us use arithmetic, addition, subtraction, multiplication, and conjugation, to calculate the real and imaginary parts of a complex number, to calculate the modulus of a complex number, to calculate the area of a parallelogram that's spanned by two complex numbers? What relationship, if any, can we find between the modulus and the argument, so the polar coordinate viewpoint of a complex number, and those polar coordinates associated with its additive inverse, its complex conjugate, its reciprocal? These are going to be really important to help us build out further the geometry of what's going on in the complex plane. And then our last couple of questions for our investigation are a little bit deeper. And so these are the ones I'm going to want you to spend the most thought on. When you're building your portfolio for this semester, your responses to these are probably going to be rich sources of material you can use to demonstrate that the material of this, this learning goal has really seeped in. So the first one is an algebraic ask for you to prove a couple of identities about multiplication of complex numbers. First, that the reciprocal of a complex number is the same thing as its complex conjugate divided by the square of its modulus. Also, that the modulus of a product of two complex numbers is the same as the product of the moduli. And that arguments, when I multiply complex numbers, arguments actually add instead of multiplication. They're going to need a couple of trig identities probably to help you out with that one. And finally, in our culminating exercise, we're going to investigate what it might look like to take the square root, not of a real number, but of a complex number, starting with an imaginary example. So you'll use our Desmos tool to see if you can figure out how to solve the equation z squared equals 2i. In other words, we would be asking, what might a square root of the imaginary number 2i be? And then try to extend that intuition to find a square root, or maybe more than one, for the number negative 9i. What about for the complex number 1 plus the square root of 3i? So in this investigation, you're going to try to come up with, discover a way of taking the square root of a complex number by using the geometric intuition that you've built in the complex plane to kind of tell you how to construct algebraically what the square root of a complex number might look like. Let me just give you a quick overview of the Desmos Sandbox that you'll be working in to do this work. So in this Desmos Sandbox, you have a couple of complex numbers on the complex plane that you can click and drag around to be wherever you like them to be. So I've got 5 plus 5i and 2 plus 0i. And in the Desmos menu over on the left-hand side, you can illuminate the sum of those two complex numbers. So now it's showing me where z plus w resides in the complex plane. Turn that off for a second. You can illuminate the difference. So there's z minus w. You can illuminate their product. So there's the product of these complex numbers. You can look at the complex conjugate of z, because that's a unary operation. W has nothing to do with it, so it's just going to show you the conjugate of z. You can see the reciprocal of the complex number z. And I recommend looking at these one at a time until you have an idea of how these things work. And once you have, for example, the product z times w on here, you can continue to move z and w around and see if you can figure out what's actually going on here. And again, as I mentioned in the previous video, we have both a rectangular coordinate viewpoint and also a polar coordinate viewpoint on everything. And I encourage you to switch if you're sort of having some difficulty figuring out what a general principle might be in rectangular coordinates. Maybe try playing around with what it looks like in polar coordinates instead. And looking at one of these at a time, I think, is the cleanest way. And as soon as you have that aha moment, what I would recommend doing is taking a screenshot or exporting an image from this Desmos worksheet. You can use this little share button up here to export an image. Hang on to that image. You'll probably be building on paper a record of the work that you're doing. And ultimately, the images you export from Desmos and your paper computations, you can capture all of those things as artifacts you can upload into your learning portfolio for the semester. So what I'm hoping is that this tool can be the main thing that you can use to do your explorations and gain your geometric intuition on what's happening here. You'll also want to try to carry out these calculations arithmetically by hand, using the real and imaginary parts or the modulus and the argument, however is appropriate for the task. So that's what our investigations are going to look like for this week. And at the end of the day, what we're hoping is that you'll be able to have symbolic representations of and arithmetic operations on complex numbers, on the one hand done with the arithmetic and the algebra, and on the other hand done in the complex plane, and that you really understand how those two things are intertwined.